Let's look at some other applications of derivatives. Some amazing math about to happen. Find the equation of the tangents to y equals x squared, which pass through 3, 8. So y equals x squared is a parabola. The point 3, 8, when you plug 3 into y equals x squared, you get 9. So the point 3, 8 is below. And there's a couple of tangent lines you can draw through that point that just touch the parabola. And we're going to find the equation of these two lines. So we're looking for y equals mx plus b. M means slope. We take the derivative and we find the slope. Now, in the earlier applications, we had a point on the line, but 3, 8 is not on the line. So what we're going to do is name this point. I'm giving it a for any value, and because y is equal to whatever x is squared, if we called x a, then a squared is our y value. So where did this come from? We needed a point on our line so that we could find the slope. We just came up with any value for x, and when we plug that any value in, we got a squared for y. So at a squared, the slope is 2a. Now, if you were doing grade 11 math, find the slope of the line connecting a squared and this point, which is 3, 8, you would have gone back to the equation for slope, which is y2 minus y1 over x2 minus x1. You can call y2 whatever you want. So I might call this one x1 and y1. And call this one x2 and y2. If we do that, sorry, it was the other way around, x1, y1. This was x2, y2. So if we do that, y2 minus y1 is a squared minus a, x2 minus x1 is a minus 3. And so there's another equation for slope. Now, we're talking about the same line. So if the slope of the line using grade 11 is given by this, and the slope of the line using grade 12 math is given by that, then we know that those two have to equal each other. All right, so let's solve this. We could multiply by a minus 3 to clear out the denominator. So that'll get rid of that. And then we'll expand this side. So 2a squared minus 6a, a squared minus a. Put everything on one side and 0 on the other. Factor it, and we know what a is. Okay, so what we know is this point right here, that's an a value of 2. And this point right here, that's an a value of 4. Now our equation, remember, was y equals x squared. So if this is 4, the y value, x squared, is 16. If this is 2, the y value is 4. Neat. Now, what were we doing again? We were finding the equation of the tangent. So what we're really doing is finding the equation at 2, 4 and at 4, 16. So that's what we're really trying to do here. So let's deal with this one first, shall we? So we're finding the equation of this line, equation of a line, straight line, y equals mx plus b. M is slope, slope is derivative. So we're finding the slope at the point 2, 4. Why am I picking that point first? No good reason. I could have done the other one. So at 2, 4, the slope would equal 4. So our first guess of the equation would be y equals 4x plus b. If we just knew what b was, we'd be done. We know the point 2, 4 is an x, y value on that line. So we could make x equal 2 and y equal 4. Yeah, that gives us 8. Bring the 8 over. We know what b is. And our whole goal was to put that in for our b values. And now we have the equation of the first line. We can check it, see if it makes any sense. So 1, 2, 3, 4 up, 1 over. That looks like a slope of 4. Does it look like your y-intercept might be negative 4? Yeah, it could be. So this is looking really good. Let's do the exact same thing with 4, 2. So what was it we were doing? We were doing y equals mx plus b. Slope was given by 2x. But this time we're plugging 4 in because that's our x, y value. All right, if this is too busy, let's just clean it up and try it all over again. So what are we doing? We're doing y equals mx plus b. Why? Because we're doing an equation of a line. We knew the slope was 2x. This time for x, we're plugging in 4. So we know the slope is 8. So we put 8 in for slope. We need to know what b is. We have a different x, y value. Okay, so put 4 in for x and 2 in for, oh, sorry, 4/16 is the point. Okay, so 4 in for x, 16 in for y. That'll give us 32. Pull that over. B is -16, so our equation 8x minus 16. We do a quick check of that one. Slope of that line. At 4, we're up at 16. Sorry, this is terrible. And 3 and 9. So are we going up 8? Oh, we're going to 3, 8, aren't we? Okay, so from 3, 8 to 4, 16. Is that a slope of 8? It is, isn't it? Because we're going up 8 over 1, so the slope makes perfect sense. And the -16, yeah, that looks like that could be pretty darn negative compared to this one. So we found the slope of the two tangent lines to here. So how is this different from what we did the other day? What you've got to be really careful of, if the point is not on the line, you have to make up your own point. When you make up your own point, you need to do the slope 2 different ways. If the point is on the line, then you don't have to do any of this, you just plug the point in. So be careful, check always if your point is on the line. What else can we do? Got a nice simple equation for the height of an object that's thrown upwards. Some of you physics people will remember that it looks like this, and we're determining velocity. How is velocity related to anything? So velocity is your change in distance over change in time. You think of driving a car, how fast you're going. It's how far you traveled and how much time it took. And this time, distance is given by height. Now, if I write change in y over change in x, you would say, oh, you're just finding the slope. So change in y over change in x, or slope, is the same as y prime. So change in h over change in t is just h prime. So velocity is the derivative of the height. So we're going to take the height, take its derivative, 100 minus 10t, and that's your velocity. That's cool. Okay, and we wanted this at 2 seconds. So at 2 seconds, you get to plug 2 in. 100 minus 20, 80 meters per second. Okay, where's the meters per second coming from? So we said velocity was change in height over change in time. And what were we measuring height and time in? We said meters for height, seconds for time. So that's how we do it. You physics people would be tempted to put all your units in, and the math people go, oh no, we trust it. It's going to work out just fine. All right, acceleration. Oof. Acceleration is the speeding up or slowing down. So acceleration is talking about how your speed is changing, so your velocity over time. So acceleration turns out to be the derivative of velocity. Ooh, how cool is that? So we're going to take the velocity, find the derivative, and that's just -10. So your velocity is always -10. At 2 seconds, -10, because the velocity, or sorry, the acceleration is always -10. Physics people, what's the acceleration? -9.8, so pretty darn close. And meters per second squared, where's that coming from? So velocity derivative, acceleration was change in velocity over change in time. Velocity from here was meters per second. So we have meters per second time is in seconds. So if I multiply by 1/seconds and 1/seconds, that will give me meters per second squared. So that's where that unit comes from. Your job today, there's more applications, and they're a combination of these kinds of things, the stuff we did at the beginning in this one. So for the non-physicky people, velocity, derivative of height, acceleration, derivative of velocity. All right, off you go.